Welcome to the virtual rollout event of the first prototype of our project Mission Pulse. Over the next 25 minutes, we're going to show you what we've been working on over the past months. But first, who is Horizon? Horizon is a student initiative founded in 2019, consisting of over 80 students from 25 countries all around the world. We have one goal: to prototype the aerospace of tomorrow. Our first project is called Mission Pulse, and since April, we are working on our first prototype, Frankenstein 1. To get more information about the project, I'd like to introduce you to Jessie. Jessie, can you tell us why Horizon wants to transport defibrillators?
Of course. An UAV, which is short for an unmanned aerial vehicle, is able to reduce the time in a life-saving way. That is because it is able to transport a defibrillator to a patient per linear distance. The aim of the project Mission Pulse is to test the feasibility of the use case through simulated test missions under realistic conditions. Our final prototype will be able to reach patients within a 6-kilometer radius in 4 to 5 minutes. At the scene of emergency, the defibrillator will be lowered with a winch under remote video supervision and can then be applied by first aiders. Before coming to our sub-teams in more detail, we will explain the certification process. Without a certified drone, we are not allowed to enable our drone to fly in real-life scenarios. Our certification and operational risk assessment will be based on the SORA process, which is defined by EASA. Johannes, can you explain to us what exactly the SORA requires to do?
The SORA process, which is short for Specific Operations Risk Assessment, defines a standard to operate inside a contingency volume. This volume includes all emergency procedures that prevent possible impacts to the ground or the airspace. A part of the contingency volume is the flight geography. The flight geography and contingency volume define the operational volume of an UAV. We want to achieve a safe operation by reducing two risks. Firstly, the ground risk, possible risks for the ground below a flying object. This means whenever there is an emergency, our last line of safety is a parachute. With this procedure, we lower our ground risk. Secondly, for possible risks in the air, we assume to operate inside an uncontrolled airspace, flying over rural areas with an altitude lower than 500 feet. By reducing those two risks, we fulfill certain categories in the SORA. More safety measures to our flight will be the determination of zonal safety, calculations of kinematic energy in case of impact, and details to our integrity and assurance level, developing a robust and secure aircraft.
So far, we learned what Horizon plans to achieve with their project Mission Pulse and what the operational requirements are. Now, let's see how Horizon plans to achieve this. To work efficiently, the team is divided into 5 sub-teams. The first one is Business and Certification. Let's talk to Sonja, a member of the Business and Certification team, and see what her tasks are. Sonja, can you explain to us what you do?
I'd love to. So in my team, besides discussing and evaluating the certification and mission requirements, we take care of all the non-technical aspects around Horizon and Mission Pulse. One of them is public relations. We take photos and videos in our workshop called the Horizon Lab, on the flight testing field, and whenever we have team events, then we publish them on our social media channels. We make sure to highlight the differences between our 5 sub-teams, and we want to show what the day-to-day tasks look like. Furthermore, we answer to all requests from press and from other students outside of our organization. Strongly connected with PR is the funding process. No money, no project. We are all students, and Horizon is a non-profit student organization. Therefore, we depend on our sponsors and supporters. We are very proud and thankful to already have so many great partners who provide all the necessary resources to work on Mission Pulse, may it be by financial support or material donations. If you are interested in being part of our project and help us realize Mission Pulse, you're more than welcome to contact us. Besides the funding activities, our team also manages budget, which means buying material on the one side and accounting all the activities legally correctly on the other side. Another task for our team is the organization of events, whether external, such as our rollout event, or internal, such as our trip to Berchtesgaden in August. We prepare and organize events to foster our teamwork in external relations. Last but not least, Mission Pulse is not only about developing a UAV which can fulfill the requirements. In the end, the mission is about saving lives. By providing the defibrillator only a few minutes faster than the ambulance, we can triple survival chances. Of course, this goes hand in hand with the application of an AED after we lowered it to the ground. So, besides looking for the perfect defibrillator, our team is also in contact with paramedical services, first responders and operators. Who is applying the defibrillator? Where does it make sense? How do we integrate it into the rescue chain in a meaningful way to complement the ambulance? We do a lot of research to find the optimal environment for our drone.
Once certification and mission requirements are determined and evaluated, our next sub-team aims to come up with a suitable drone configuration for our use case. Here's Philip, sub-team lead of our design loop. Their team consists of 15 students, most of whom are studying aerospace. Philip, can you tell us a little bit more about how you come up with a suitable drone configuration and what are the main aspects that you have to consider?
The key design drivers for the eVTOL are based on mission performance, such as cruise speed, altitude, takeoff mass and range. We also consider the certification part. For example, the redundancy. There must not be any single point of failure in the system. For finding a final drone configuration, we divided our design process into a conceptual and a preliminary design phase. In the conceptual design phase, we compared different drone configurations like a helicopter, multicopter or different fixed-wing configurations. These configurations were rated by aerodynamic efficiency, modularity, masses, safety, complexity and further criteria. Based on this rating, the most suitable configurations were pre-selected and the first missions calculations were conducted. Based on numerical values, the best configuration was selected and investigated in the preliminary design phase. As a result, for Mission Pulse, we decided to use a fixed wing configuration with separated rotor systems for hover and cruise flight. One of the biggest challenges in aircraft design is that all design parameters influences each other. For this reason, we built our calculation methods as a loop to iteratively determine the final configuration. This is also where our sub-team name, Design Loop, comes from. For the preliminary design, we split the different design disciplines of the aircraft into the following 5 sub-modules. First of all, in the flight step module, the trajectory is generated based on the mission segments and operating conditions. Out of the trajectory, we determine the different flight states of our mission. In the aerodynamics module, the forces and moments on the lifting surfaces are calculated. Afterwards, based on the forces and moments, the structure of the drone is determined to withstand the bending and torsion of the wing surfaces. Out of this, the masses of the wings and empennage is calculated in the structure module, which is our third submodule. In the performance module, the mission required thrust and power of the propulsion units are also calculated. Within this module, suitable motor, rotor and powertrain configurations, as well as the battery system, are selected out of a database based on torque, efficiency and masses. Finally, in the geometry module, the modified geometry out of the calculations is modeled. All submodules are self-coded in MATLAB and Python, and the whole loop is integrated in our toolchain managed software RCE. The final configuration has a span of 2.55 meters and the takeoff weight is approximately 17 kilograms.
We just learned that the design loop team iteratively repeats their calculations until a final design is fixed. With that final configuration, the next sub-team can keep working. This is Kevin, our head of CAD. Kevin, can you explain to me what you do once design loop forwards you their final results?
Yeah, of course. So we get the final drone configuration from the design loop team, and our job is to model and design a prototype. And for the Mission Pulse project, the prototype's name is Frankenstein 1. And most of our work is actually in front of the computer. So we take the theoretical values that design loop gives us, and we transfer or translate that into a model through computer-aided design. And our job ends with delivering molds or tools to the structure team for them to start their manufacturing phase. The most challenging part of this process is to find technical solutions that are within our weight budget, economically viable and compliant to our manufacturing method, while still maintaining structural integrity in regards to the forces on the aircraft. Each section of the aircraft also requires different design solutions, as the forces or weight requirements are different, presenting varying levels of complexity in each design process. As an example, the biggest challenge of the fuselage is to integrate the number of subsystems, such as the electronic plates, the rope mechanism, and the warning system. They all require sufficient space, specific positioning, and a suitable mount to the fuselage. A big organizational challenge, on the other hand, is the coordination between the sub-teams, which often prove to be the bottleneck slowing our design process. Our way to tackle these challenges, while still trying to meet our deadline, is to subdivide the drone to sub-assemblies. Therefore, we have the field's fuselage, wings, tail, and hover boom, and assigning 2 or 3 team members to each sub-assembly allows a parallel workflow, while still having long brainstorming sessions together to tackle the bigger problems. For problems that we cannot solve ourselves, we implemented a technical review meeting where representatives of all sub-teams and advisors are present. We also decided to delegate the aesthetic design work to a professional design company, which allowed us to focus on the engineering process purely. We are very happy and proud to have contributed to the team, and we're very grateful for the experiences we gathered along the way.
That sounds great so far. So we have a certification and mission requirements. We have a drone configuration from Design Loop and a 3D model of our prototype Frankenstein 1. By the way, if you're wondering where the name comes from, feel free to come by our lab and ask us. This is also where the physical work gets done. Here are Osama and Cosima from our structure sub-team.
Welcome to the structure team, where we build the prototypes in our workshop. We would like to give you a glimpse of our work in the workshop by taking you through the manufacturing processes. When the CAD sub-team finishes their models, the first step is to get the epoxy boards milled to form our master blocks. The master block looks very similar to the final part. Once we finish sealing the surface, the master block is ready for the tooling prepreg. Tooling prepreg is a specific kind of pre-impregnated carbon fiber textile, which is used to create the tool. We drape the tooling prepreg perfectly onto the master block and apply vacuum between the layers to get rid of any entrapped air. The master blocks are then put in the autoclave, a large pressure vessel that uses high temperature and pressure to cure the tools.
Once out of the autoclave, the tool is removed from the master block and serves as a negative mold for our final parts. Similar to last year, we are hand laminating our parts. However, this year we are also using carbon prepreg for our layup. We use a combination of foam, carbon, and glass fiber layers to achieve a good stiffness while keeping the weight as low as possible. We put in extra reinforcement in certain places where the loads will be especially high. The part itself is also cured in the autoclave. The finished parts are then assembled using a variety of connectors. Finally, the drone is ready to get tested by our flight testing team. If you want to find out more, come visit us in our workshop.
Some of our members are also working on subsystems, such as the parachute and rope mechanism.
Another crucial system is the rope mechanism, which is designed to lower the payload safely and reliable while the drone is in hover flight. The challenge with this is to guarantee a soft landing during every deployment and various environmental conditions. The use of a servo motor enables the pilot to manually control both the deployment speed and deployment direction to account for different ground conditions and also weather conditions.
We are almost at the end of our day-to-day operations. When Structure finishes the manufacturing, the prototype can be tested by our final sub-team, Avionics and Flight Testing. They only have one goal, to finally make Frankenstein 1 fly. Aurora, is that correct?
Yes, absolutely. And by testing the prototypes, we get to see how everything works together after a whole year of work. To complete the task we defined for Mission Pulse, we need various systems to work together, including hardware and software. Things can get very complicated quite fast. Therefore, we always start simple and increase complexity gradually, because building the whole aircraft and hoping that everything works at once is not efficient. Failures will definitely occur. So we integrate and test various subsystems on dedicated prototypes before putting them all together for Frankenstein 1, our first prototype. We use quadrotors and small eVTOLs to test the software we develop and bigger prototypes to test heavier systems such as the parachute or the rope mechanism. We prepare our prototypes in the workshop and as soon as they're ready, we conduct flight tests to verify the correct working of the drone and of its subsystems. Before going to the flight field, some preparation is needed. We use checklists to make sure not to forget anything and to follow the procedures in the correct order. On the flight field, there are several roles. The flight manager goes through the test card and makes sure that all operation runs smoothly. The operator is the person in the ground control station that monitors the flight data and guides the pilot, who flies the aircraft. Finally, there is a flight engineer who checks and assures the readiness of the aircraft. After each flight, we evaluate the performance to improve or to validate the setup. Although a lot of experience with flight tests has been gained in the last year and procedures have been optimized, flight tests remain time-consuming and costly. To shorten the time on the flight field and eliminate simple errors, we set up a hardware-in-the-loop. This so-called HIL allows us to connect all subsystems first before testing them on the real aircraft. We can test individual components all the way up to the entire wiring harness. With additional equipment, we can monitor signals, currents and voltages to easily find errors. With the HIL, extensive ground testing can be performed on all subsystems before they are integrated into the overall system. This reduces the likelihood of potential costly crashes. We are working on several projects to improve the capabilities of Frankenstein. The aircraft will fly beyond visual line of sight, which requires a robust data and video stream over long distances. We develop custom electronics for high current and voltage application to increase safety. Moreover, we work on our own flight control software to get the most out of our configuration, and we use state-of-the-art tools to make accurate models of our aircraft. To automate the whole mission, we deploy artificial intelligence algorithms, which reduces the operating workload so that the pilot only needs to intervene in case of emergency. For testing those new features, we are building a simulation environment, which will be used to reduce time and cost-intensive flight testing for testing rather simple and basic features.
So, after visiting all of the subteams, we're at the end of our little tour through Horizon. The prototype which you're about to see is the result of long days and nights, of weeks and months of dedicated work. But when a team spends so much time together, the result is no longer just to get a working prototype into the air.
Horizon is not only a team, it's also a family with many different characters, where everyone has their reason why they are part of Horizon. For me personally, Horizon is the aerospace of tomorrow.
Innovation,
Flexibility,
trust, ambition,
our common goal,
Spontaneousness,
passion,
learning,
inspiring,
international, history, fun,
growth,
Responsibility,
perseverance, flying planes,
Opportunities, night shifts,
future,
bouldering,
saving lives,
challenges, integrity,
dedication, diversity,
innovation,
teamwork,
life-changing,
friendship,
community, united,
family.
Finding solutions.
So finally today we are here after 1 year, and for me what is the most important thing is that actually not everyone gets the chance to show their work to such an audience, and not everyone gets the chance to work in such a beautiful team. So this is the most important thing for me. I'm just enjoying the moment because probably 1 year after that, or even tomorrow, we will be like, oh my god, that was amazing. So I'm just trying to enjoy the moment. It's fine. Yeah.